Good morning, everybody, and welcome back. I'm going to start the new year anyway in the way that you hoped that I would, with some videos. So basically, here's the deal for the next little chunk of time. We have 3 things to talk about. One of them is finding the length of an arc, which is what we're going to do today. So I'll talk about that in a second. The second thing is to move on to parametric equations and the calculus behind them. And the third thing is to move into polar. So if you remember, parametric and polar, what did we even do last year? Don't even know if I guess we wouldn't have talked about them last year at all. You would have talked about them in pre-cal. So parametric equations are things where you have like x of t equals 2t and then y of t equals 5t plus 1. 2 separate, can you see that in the shadow? Yeah, 2 separate equations telling you what the deal is with x and what the deal is with y based on time. I will go over all of that tomorrow or our next class. And then we're going to be dealing with like the derivatives of them and the integrals of them. Kind of cool, actually. I really like parametric a lot. Then after that, we'll move into polar. If you remember, those are the limacon curves and the cardioids. And sometimes you have an inner circle, sometimes you don't. Those are polar curves. Those are things that are like theta equals sine r, or sorry, not that way, r equals sine theta, and things like that. So we'll go over all of the polar stuff and remember that, and then we'll have to talk about the calculus of it, derivatives and tangent lines and such. So yeah, it's going to be fun. It's kind of cool. So that's what we move into. After we just do all of that, we talk about improper integrals. And then sequences and series. And these are nuts, totally bananas. But they're awesome if you have that interest in pure math. So I love series. They're just really, really weird. And then we're done. Then we'll be basically done with info. I think there's a couple little topics I have to throw in, like little tiny things. One's called Euler's method that we didn't talk about yet. We'll make sure we go over L'Hopital's rule. And then we'll start to review. So I'm thinking like this takes us through January probably. This takes us February and a little bit of March potentially. And then we, fingers crossed, have all of April to review. I know there's spring break in there too, and maybe even a little bit of March. So giddy up, very exciting. So in terms of grading, right now, I'm still trying to see what I think, but right now we're gonna have little grades. So for example, there's a Khan Academy assigned today. That's gonna count for a little grade. We're gonna do little spot check quizzes along the way, like a 1-question warm-up. Those are gonna count along the way. So right now, I'm not going to be worrying about big tests this marking period. Right now, I'm going to be worrying about little checks, maybe even throwback checks, and I'll let you know when those come in, but that's where I'm thinking. So anyway, to ease you into 2021, we have a very simple topic for today, and that is how to find the length of an arc. We are not talking about anything parametric today. We are not talking about anything polar. We are just talking about how do we find the length of a regular arc. So let's say we have a parabola. How do I find out how long the arc is, let's say from 0 to 2? Literally, how long is that? If I were to trace this with a string and then measure how long the string is, how long is that arc? So this is something, you know how to take the arc length only of one thing so far, and that's a circle. So you know how to find the arc length of a circle because we have a circumference formula. Circumference equals 2 times pi times r. So if I had a circle, that would be how I would find the arc length, or the length of part of that circle. But now I'm going to apply it to any kind of curve. So the basic formula for it is this. And I'll show you where it comes from. To find the length of an arc, we're going to take the integral from a to b, so from, let's say, 0 to 2, of the square root of 1 plus the derivative of the curve with respect to x squared. dx. This is the formula. So if I were trying to find the arc length of y equals x squared from 0 to 2, I would have the integral from 0 to 2 of the square root of 1 plus dy dx squared with respect to x. So in this space goes the derivative of y with respect to x, so in this case 2x. And that's it. I would put this in my calculator and I'd get a numeric answer. I didn't do that. I don't, whatever, I will, because then I'm going to feel bad otherwise. Menu, calculus, integral, 0 to 2, square root 1 plus, I usually end up doing that for x squared dx, and I get 4.646. Remember, you always have to give those 3 decimal places. Connor, not to point you out, I think it was you, but my memory could be totally wrong, that on the test wasn't giving 3 decimal places. You've got to give 3 or you don't get the point for it. That's it. It literally is that simple. So it's very rare that you wouldn't have a calculator for this, because this is most, like 99.9% of the time, not something you can integrate by hand anyway. So you would need a calculator to get the integral. So that's it. So I'm going to show you where it comes from, but I also want to say you probably want to start keeping track somewhere, having like a little formula sheet going, maybe the first page of your notebook, maybe put like a little sticky on it so that you can keep referring back to it. Let this be the first one and then leave space, probably leave another page or 2, because we're going to keep accumulating formulas that you want to be able to like look back at quickly. So this is the first one, how to find the length of an arc. This is the only thing we're going to do with regular rectangular functions. We're going to move on to parametric, and I could totally move on today, but I just thought, whatever, we'll keep it light. Tomorrow we'll move on to parametric functions. So this is it. This is the crux of what you have to do. It seems so easy. You'll start to forget this formula because we'll go so heavy into parametric that you'll forget that an arc length formula existed for non-parametric. So when you put this formula down, you also want to say non-parametric, because so much of what we'll do coming up will be parametric and you'll forget. Okay, so then just the question of where the heck did this come from anyway? And then we'll do one more example. Let's just give myself a more general arc. And let's say I wanted to take like the length of it from there to there, from A to B. If you think about what this looks like, and you think about zooming in on a little tiny piece of it, if I have like, if I just want to figure, okay, how much is this much? I have a change in an X and I have a change in a Y to represent this little tiny bit. So like this little tiny piece is a change in Y and a change in X. And this is like the piece of the arc, if I can think of it as like minusculely small. If I can think of dx and dy being like limiting to 0, being as small as possible, then this little section here is the change of the arc in a little tiny way. And what I'm going to do is I'm going to accumulate, or take the integral of, integrating accumulates lots of little things. I'm going to accumulate an infinite number of these little tiny sections. So this section can be thought of as, with Pythagorean theorem, this is a right angle. Dx squared plus dy squared, the square root of that is this. So this is going to be the square root of dx squared plus dy squared. That's how I would find this little tiny arc. So I'm adding up an infinite number of these guys. So this is what I'm doing. But how do I get it to look like this? Well, then there requires a little bit of algebra. I'll mess with it in a second. But just to explain again, this little tiny section is like part of a little tiny right triangle with a change in x and a change in y. And if I can just find that hypotenuse with Pythagorean theorem, I can use this to represent this little section. And I can add up an infinite number of those little sections and get the length of a curve. Because each little section, even though it's like a straight section, it's so tiny that when I add up an infinite number of them, I end up getting the curve. So this is what you're doing, but I am going to do a little bit of manipulation to get it to look like this, because this is dx and dy, and so that's going to be a little bit complicated. What I would do is I'm going to pull a dx squared out of this. So I'm going to take a dx squared out and be left with 1 here. And how do I take a dx squared out of something that doesn't have a dx squared? Well, I basically multiply this little guy by dx squared over dx squared. So when I pull 1 out, what I have left is the dy squared over the dx squared. Then this dx squared is inside of a square root, so this just becomes dx. This stays under the square root as 1 plus dy dx squared. And now I have that. If that didn't make sense or whatever, it doesn't really matter. All you need to know is the formula. So let's just look at one more just to make sure that you're comfortable. So let's find the length of sine of x from x equals 0 to pi. So let's find the length of one hump of sine of x. So sine of x goes like this. I'm just looking at this part to this part. How much is one hump? So I'm just going to use the formula. Go from 0 to pi, square root 1 plus dy dx squared with respect to x. So be careful. You always have to take the derivative of the function. That's what goes in this spot. So the derivative of sine is cosine. And that's it. I'm putting that into my calculator and I'm getting numeric answer. I don't have it written down here, but it should be something like, I think it's something like 3.8 something. You can go and check that if you want, but whatever, you're just putting that into your calculator. You might want to double check because people get confused how to put cosine squared in their calculator. You can't put cosine squared x, even though you could write it like that if you wanted to. You can't put it like that in your calculator. You need the parentheses and a squared on the outside. So you might want to just practice putting that in. Okay, so your assignment for today is to go do a Khan Academy. It should be assigned. And it should be easy, and it's called arc length. And that's it. And I will give you points, and then we will all be happy. Yay. All right, I know motivation will start to wane as you've gotten college acceptances or whatever, and we're nearing, I guess we have until the second semester starts before you really start to check out. So, oh gosh, I guess I have to do everything in the next 2 weeks. Just kidding. That's it. All right, have a good day.